Welcome everyone, my name is Sultan,
And my name is Shannon.
and our project involves converting a remote island to renewable electricity, specifically Stewart Island. In today's short video, we will outline the problems associated with small islands and explain the key aims of the project. Following this, the demand predictions shall be outlined to coincide with the energy and resources evaluation, including the methodology, results, and discussion. Islands and remote coastal areas currently meet their energy requirement using submarine cables or using fossil fuels. This makes the island highly vulnerable to fluctuating fuel prices. Such islands require a localized energy system that uses the limited natural resources, hence decreasing their reliability on the mainland. This leads to the aim of this project, which is to develop a framework for these communities to supply 100% renewable electricity, exclusively using the pre-existing resources. Stewart Island was selected as a case study to coincide with New Zealand's ambitious goal of 100% renewable electricity by 2030. Stewart Island is the third largest island in New Zealand, situated approximately 30 kilometers south of the South Island. As of 2018, Stewart Island had a population of 408 residents, with approximately 30,000 tourists visiting annually. The island consumes about 360,000 liters of diesel per year to generate electricity. There are several interesting aspects of Stewart Island which increases the complexity of this case study. Firstly, the island population is exceptionally small, and secondly, the island has an area of 1,570 kilometers squared, of which 85% is classified as a national park, which significantly restricts the access to available resources.
Two different scenarios have been developed to predict the electricity demand in 2030. Scenario 1 represents an estimated maximum demand based on assumed growth in a variety of sectors. On the other hand, the second scenario represents an approximate minimum demand, which utilizes historic data to project to 2030 assuming linear behavior. The first scenario was used as the foundation to design the energy system to increase the applicability to other islands. This demand was fitted to a typical 24-hour trend so it could be used for the evaluation. To complete this evaluation, firstly, hourly data was collected from reliable sources. Secondly, the variability of the resources was analysed. The third step is to evaluate the electricity generation, which can be compared to the demand to get the system reliability. This allows for sizing of any backup system needed. Lastly, the economics need to be evaluated, specifically the levelized electricity cost.
If we look on a daily basis, there is significant fluctuation with numerous days where the generation is insufficient. To increase the reliability of the system, demand response can be used by adjusting the demand to the electricity available. In the case of Stewart Island, the demand can be changed in March, where generation is low, by encouraging the salmon processing plant to shut down for maintenance, which will coincide with the end of their big harvest. The demand can only be adjusted to a certain extent, therefore the second option is to create hybrid solutions.
After finding the hybrids, the levelized electricity cost and reliability for the different solutions was modelled. This cost was compared to the 2018 price and the minimum 2030 predicted price using diesel. Doing this highlights two things. Firstly, the trade-off between reliability and the cost of electricity, and secondly, the optimum solution. What we're really interested in is the solution that achieves 100% reliability at the lowest cost, which in this case is an onshore wind and wave hybrid. This oversizes the system from a generation perspective, but is cheaper than relying on storage. Although an onshore wind and wave hybrid is the optimum solution, a backup system is required for 100%. Using batteries results in a price of 64 cents per kilowatt hour. The other option is to repurpose the existing generators and use biodiesel. The maximum price that biodiesel could be is $23 per litre to be cheaper than batteries. There remains a trade-off using biodiesel that is a 6% reliance on mainland energy and carbon emissions. To put that into perspective, they are currently 100% reliant on mainland energy and emit 979 tonnes of CO2 per year. And so we come full circle for powering Stewart Island with renewable electricity. Application of our energy and resource evaluation methodology successfully demonstrates the trade-off between reliability, cost, and fuel independence.
Although each island is case-specific, the framework developed provides clear guidelines to assist in the identification of the optimum solution.
Thank you for watching. For more presentations, please scan the QR code.